Okay, this is Mr. Asher, and this is for Chem 121. And this is an optional video that I'm recording to walk you through how quantum mechanics is related to the structure of atoms, the electronic structure of atoms. And so I wanted to go through and talk a little bit about the historical development. So along around the late 1800s, 1890, 1894, there was a lot of stuff known about atoms, and how they worked was not fully understood, at least in terms of the classical physics of the day. And one of the things that was puzzling to the sciences was something called atomic line spectra. Now, everything glows and emits light if you heat it up, but if you heat atoms up, pure atoms up, an element up, then what happens is it gives off light. And if you heat it up, it doesn't give off an entire spectrum of light. Light comes in different colors. And this is an example of the full spectrum of light, all the way from red out to purple. And of course, there are wavelengths that go on beyond that, ultraviolet, and wavelengths that go beyond that to the left here, infrared. But we tend to see in the visible, so we tend to think of light as just being visible. Well, anyway, if you just heat up a piece of iron and let it glow, it gives off all of these different colors. But if you heat up iron atoms as a gas, something funny happens. Or if you heat up any atom, and what happens is that it gives off light only at specific wavelengths or colors. And wavelength determines color of light, at least in a vacuum. And so, for example, this is hydrogen, which is atomic number 1, so 1 proton, 1 electron. If you heat it up, what you find is it only emits this red light, blue light, and then these two purple or violet bands. And that's the only wavelengths it gives off, and it doesn't give off all of these other colors, right? And it gives off more wavelengths up here in the ultraviolet and some down in the infrared, but these are the ones that we see as visible. Helium has all of these bands, and here is mercury, which looks here, and then uranium has all of these bands here. So uranium is almost giving off a full spectrum. But anyway, why atoms should be giving off light at discrete frequencies wasn't known, or wasn't understood. And it turns out that every element, and here's an example of the periodic chart with the line spectra of each element given in this little square, every element has its own unique characteristic emission spectra. And so it was a real puzzle as to what was going on, especially given the understanding of the atom in that time period. Now, we talked about this sort of solar system model of the atom just a little bit, where you have the nucleus, where you've got the protons and neutrons and most of the mass, and then the electrons are contained in these sort of orbits around the atom. And there's a problem in terms of classical description of the atom in this model, that if you have an electron in a circular orbit, that it isn't stable, at least under classical physics. That what happens is the electron would have to emit energy in the form of photons, and then as it emitted that energy, the electron orbit would decay until finally it intersected with the nucleus, and then the electron would combine with a proton to form a neutron, and that would be the end of the atom. But that doesn't happen. And so to rectify this situation, what Bohr said was, he said, well, let's assume that these electrons are confined to particular radii around the atom and these shells. And we talked about these as the principal quantum number n equals 1, and n equals 2, and n equals 3. And he said electrons are confined to these shells. And what happens then is the emission spectra that we see are because electrons are jumping between these discrete distances between the atom. And when he did that, he found that he could model precisely the emission spectra for different atoms using this shell model. But he didn't understand why electrons should be confined to these different specific radii. And he didn't understand what he was seeing, at least not at the time. And by the end of his life, he understood it quite well, and he was able to explain it all in terms of quantum mechanics. So these line spectra were puzzling. And this solar system model of the atom, which seemed to be correct in terms of what they knew about the physics, they knew that the nucleus contained most of the mass and the electrons are distributed around the nucleus. And this shell model of electrons seemed to be a great way to describe what was going on, but they didn't understand why that should be. Well, let's take a step back and talk about some physics experiments that were being done around the same time. And one of them was called the photoelectric effect. And what happens is in the photoelectric effect, if you shine photons at a metal surface, below a particular wavelength, and red wavelengths are longer than blue wavelengths. And so as you go to red, if light starts out as red, then you shine that light on a metal surface and nothing happens. But as the light gets bluer, it goes to shorter and shorter wavelengths. Eventually you get a threshold, a wavelength, at which all of a sudden electrons are ejected from the metal surface. And this was puzzling to scientists because before this, we'd assumed that light behaved as a wave, as an energy propagating wave containing energy. And it was thought that if the light contained energy, that any amount of light energy hitting the surface should be able to eject electrons from the surface. But it looked like that there was a very definite frequency at which, or wavelength at which all of a sudden light had enough energy to kick electrons off the surface. And this didn't quite fit with the model for light in the day, but then there were some other puzzling things about the photoelectric effect that weren't understood. And one of those was that not only was there this threshold energy level above which you didn't get electrons, but that when the electrons came off, they came off with a kinetic energy. I mean, they came off with a speed that was determined by the wavelength of the light. And that was completely puzzling. So if you look at this in terms of a plot, what you find is if you look at light frequency versus electron kinetic energy, the electron kinetic energy is zero, meaning there's no electrons until you get to this threshold. And then the kinetic energy increased linearly with the frequency of light. And so it seemed it was apparent that light was carrying energy as a function of wavelength, which wasn't really quite understood how that would be. And then not only that, but if you looked at the electron current as a function of light frequency, if the light intensity remained the same, the electron current remained constant as a function of light frequency. And the current was only a function of of the intensity of the light, meaning that you got the same number of electrons coming out once you're above the threshold, regardless of the frequency of the light. It's just you got more of them. And you got the same number of electrons coming out. It's just as the frequency went up, they had more kinetic energy. And so that started to make people think that light was behaving not just as a wave, but as a particle. And then the concept of the photon came out. And so then they realized that light had both properties of a particle and as a wave. And that got in the concept of this wave-particle duality, which is fundamental to quantum mechanics, that a photon could behave in some senses like some instances like a wave, but also carried properties of a particle. And that got scientists at the time thinking about this idea and how they would represent a particle that had both wave characteristics and particle characteristics. And then, at the same time, people started looking at how electrons behaved. And they started doing things called electron diffraction experiments, where they would shine electrons, they would get electrons, and they would accelerate them through two slits. And when they did that, they formed interference patterns, just like waves diffracting through a slit would have. And so they began to realize that electrons displayed, just like light particles did, both wave and particulate properties. And once that was realized, and then here's a picture of an actual electron diffraction spectrum where electrons are diffracting through a grid, and you see these sort of bands of light and dark where the electrons are diffracting through. So it was known now that electrons could behave as waves, and that led to de Broglie in 1924 to come up with the de Broglie wavelength of an electron, where he came up with this de Broglie wavelength lambda, which was given in terms of this constant h, which is called Planck's constant, divided by the momentum, which is mass times velocity. And once they calculated the wavelength of the electron, they realized that what was going on was the electron was behaving like a quantum mechanical particle. And so people started developing quantum mechanical descriptions of the atom and of electrons and calculating things like wavelength of the electron in an atom. Well, if you do that and you assume that the wavelength has an electron, what that means is it sort of exists as a propagating wave with a wavelength that looks like this, right? And this would be the one integral wavelength. So one electron would have this sort of wave characteristic, right? Would have a wavelength like this. And what this is sort of a construct, a mathematical construct where it has to relate to the physical position of a wavelength. But the point is that now electrons in space, if you're going to confine them in space, have to be in space where they can have an integral number of wavelengths, because this end here has to match up with this end here, right? So if you have multiple electrons, they all have to go nose to tail. Or if you have one electron, this part here has to mate with that electron, that part there, to fully complete the one wavelength. Well, if you think about this, this is one wavelength represented in a linear place, but what if we bend this line here around to mate up with this line here and make it into a circle, right? So that's what I've done in this plot. So you can see here's the start of the electron. Actually, it would start here where it's high, and then it goes around in the circle in the wavelength and comes back over here. So this is this wavelength, one wavelength in a circle, right? And here's the blue line, which is starting low and going high. And so what you see here is now around the circle, I can fit one wavelength of the electron, right? And it can be in two particular places. It can be here, where it starts out high and goes low, or here it starts out low and goes high. And that's just a manifestation of the quantum mechanical behavior of the electron, that it can start, that it had that integral number of wavelengths. If you're going to put them in a circle, there's only a certain number of positions. Well, let me come back to that. But anyway, this is one integral wavelength around a circle. But what happens if we look at two wavelengths? So here you can see I've got one wavelength to here and a second wavelength to here. And now we're going to bend this around in a circle. And now the pattern looks like this, where here is the first wavelength, starts high, goes low, comes back to high. And here's the second wavelength, high, low, high. And here's the opposite, starts low, goes high, comes back to low, starts low, go back to high. So that now I've got these two different patterns. But now if I think about it, I can also put an electron in a half wavelength. So like an electron can be here, or it can be here, or whoops, it can be here, or it can be here, or it can go all the way around in that whole circle, right? So now when I have two wavelengths, I've got two positions that the electron can be in. It can be here, it can be all the way around, or it can be here. So there's two different places the electron can be. Well, let's look at three integral wavelengths. So three integral wavelengths, so there's one, there's two, there's three. And if we bend that around in a circle, it looks like this, right? So now the electron can be starting high, going low, coming back to high. It can be in that one wavelength, or it could start low, come to high, start low here, so it could be there, or it could start high, there to there. So it's got those two options, or it could be in the full circle around again, or it could exist in one integral wavelength, here to here to here. So here it's got three separate places it could be, right? It could be in the full revolution, it could be two wavelengths, or it could be in one wavelength, right? And now the size of these circles that they're occupying is going up as the number of integral wavelengths that the electron can exist in go around the circle. But not only is the size going up, but the number of places the electron can exist goes up, right? So if we draw this all the same, here's one wavelength, here's two wavelengths, here's three wavelengths, and here's four wavelengths. Okay. So as the number of, so you can see that as the number of wavelengths goes up, the diameter of the circle increases. And now we're starting to look sort of like the Bohr model, where you've got an electron can be in different integral places around the nucleus of the atom, and it can't be in between here. So it's confined to be in a particular location around the nucleus. And if we look at this, whoops, not fancy. And if we look at this, we see that here's our diagram. For one wavelength, there's one position for the electron. Well, two positions because it can be in the red or the blue circle, but one position in the nucleus. At two wavelengths, there's two positions. It can be all the way around, or it can be in a half a circle. For three wavelengths, there are three positions. It could have one wavelength, it could have two wavelengths, or it could be all the way around. For four wavelengths, there's four positions because it could be all the way around, which is four wavelengths, or three wavelengths, or two wavelengths, or just one wavelength, right? So as the number of shells go up, the number of positions where the electron can be go up. And if you think back, right, so here is it again, and I'm sorry that my head is blocking this. We can talk about these as these elemental or these index numbers, that n equals 1 is one wavelength, n equals 2 is two wavelengths, n equals 3 is three wavelengths, n equals 4 is four wavelengths. And now if we think back to our principal quantum numbers and addresses, and we look for n equals 1, there is only one place for the electron to be, just like in here. N equals 1, there's one position. For n equals 2, there's two positions. It can have L equals 0 or L equals 1. And here, for n equals 2, there's two positions. Whoops. For n equals 3, three wavelengths, there are three positions, just like for three wavelengths. And for n equals 4, there's four wavelengths, just like in 4. So what's going on with these principal quantum numbers is this principal quantum number is quite literally the number of integral wavelengths around the nucleus that the electron can have. And what these numbers are specifying is what type of orbital that is in terms of whether it has 1, 2, or 3 wavelengths in it. And that's why they get so complicated in shape as you go up in L, because it's reflecting the fact that it can be partially around the nucleus or partially not. But they're sort of more complicated than that. But that's kind of what's going on. And this spin number -1/2 to +1/2 is the difference between this blue circle and the red circle, that it can be positive or negative, and that's plus or minus surface. So hopefully this isn't too confusing. I wanted to give you a little bit of physical context of what was going on. There's some very complicated math associated with all of this. You'll hear it called Schrodinger's equation, the wave function of the electron. I don't think that's particularly useful here to understand. I think you can get kind of a sense of what's going on from this sort of very simplistic view of the physics of what's going on in terms of integral wavelengths of the electron. Anyway, hope you find that useful. I'm going to stop there and talk to you later.